Hi, I'm Qing Sun from University of Delaware. Today I'm going to talk about the paper we just published in ACS Nano named Post-Translational Modification of Bionanoparticles as a modular platform for biosensor assembly. Detection of analytes, including pathogens, toxins, or cancer markers, are essential for human health and safety. Biosensors function by converting the recognition of analytes into actuated signals. A functional biosensor will require the input module like antibody or aptamers, output module like enzymes or fluorescence dyes, and at last a scaffold to organize them. In terms of scaffold, protein nanoparticles have a lot of advantages. First, they are nanoparticles, so they have the high surface to volume ratio, and they can self-assemble into uniform bionanoparticles when protein folded correctly, so it's a bio-friendly synthesis process. However, to make bionanoparticles ideal platform for biosensor assembly, there are several problems to solve. First is the decoration of bionanoparticles with the input and output module. The first method is chemical modification. However, this method lacks the control over the orientation and ordering of all the components, might lead to the functional loss of the components. Second method is genetic fusion. However, it might lead to the aggregation of nanoparticles. The last one is click chemistry, but it's very expensive. Other than bionanoparticle decoration, bionanoparticle purification is another problem. The traditional way of purifying bionanoparticle, including ultracentrifugation and filtration, are quite tedious and time-consuming. So the strategy we propose to solve this problem and make bionanoparticle ideal platform for biosensor assembly is post-translational modification. So we can express the bionanoparticle and all the other sensor components separately, and that ligates them back together with orientation guaranteed manner. Southeast A was proposed. It is a transpeptidase which can recognize LPETG tag from C-terminal of one protein and triglycine tag from N-terminal of second protein and form the covalent attachment. With this Southeast A ligation platform strategy, we can use them to first ligate a purification tag onto the scaffold, onto the bionanoparticle for easy purification, and then sequentially ligate all the other sensor components to form functional biosensors. The number one advantage of this system is easy purification.
Elastin-like polypeptide forms hydrophobic aggregates when temperature increases and salt is added, and they can get resolubilized again in cold buffer. The process is reversible and it is utilized to apply for easy protein purification. We incorporated ELP to E2 nanoparticles, and this enables us to purify E2 nanoparticles within 1 hour.
With this purification platform, we were able to move ahead and construct our biosensors. Number one advantage of this biosensor platform is signal amplification. Because with this sequential decoration method, we were able to control over the decoration efficiency of each modules, and were able to get up to 22-fold enhancement of signal amplification. Number two is the modularity of this system. First, we were able to use antibody as the input and enzyme as output to detect cancers. Then we were able to replace enzymes with fluorescence dye to visualize the cancer cells as it's shown. At last, we were able to replace antibody with aptamer to show the to use as the input for cancer detection. With the modularity show, the overall achievement of our sensor is easy purification platform, signal amplification, and modularity of 2x2. But this system is very flexible, so we can expand the modularity to higher level, and also we can think about using this platform for other applications like drug deliveries. Thank you for listening. So any question, please refer to Dr. Wilfred Chen in University of Delaware.